Okay, here we are with chapter 5. We went through measurement, we went through problem solving, went through vectors. Last chapter, finally, we got to the physics and we talked about motion and how we describe motion with velocity and acceleration, and even how we can use those to predict a location after a certain amount of time in one and two directions, two dimensions. And now we're going to talk about the things that cause motion, right? We focused on describing motion last chapter. This chapter is about how does motion happen and how does motion change more exactly. So this chapter is about forces. And I don't know what you think about when you think about forces, but some people think about Star Wars and Yoda, and that is not the right way to think about forces in this chapter. The stuff in Star Wars is not accurate to real world physics, and so please don't think about it in that way at all. It'll just confuse you. So forces, what is a force? That's the first question. So what exactly is a force? And in the past, I've given my high school students the extra credit assignment to go home and find me a force that was not a push or a pull. And they came up with all kinds of things, but none of theirs were correct, because that is the definition of a force. A force is either a push or a pull. So as we can see in this picture, we got one kid pulling the wagon, another kid pushing the wagon. When you push or pull something, you are applying a force. You are putting forth effort to try to cause that object to move, or to try to cause it to stop moving, or to hold it up, or whatever the case may be. But it all comes down to a push or a pull. As we'll learn in a later chapter, sometimes this is described as tension when something is being pulled, or compression when something is being squeezed. But for now, a push or a pull is a good enough definition for us. And when you push or you pull, you have to push or pull in a direction, right? It has to be going in some direction. You think about different ways of pushing, right? You can ball up your fist and you can push with your fist. You can throw a punch in some direction, but it has to be in a direction. If you ball up your fist and then you tell somebody punch, but don't punch in any direction, they'll look at you funny, right? There's no way to do that. So forces have direction, which means they are a vector. And of course, they obviously have size. So a bigger force would be a longer arrow, a smaller force, a shorter arrow. Forces also are a little unusual in that they can either be at a distance or they can be by contact, right? Most of us think about contact forces, right? If somebody pushed us or if we pulled on a rope, that would be contact. We would be touching in order to apply that force or to deliver that force. But gravity is a force that can work on us without touching us, right? If you lose your balance, you fall toward the earth. Even though you're not touching the earth is still able to pull you downward. And of course, friction is a great example of a contact force, because that's how you get friction, by two surfaces in contact with one another while they are trying to move past one another. So in physics, we have over the years come up with four fundamental forces, four main forces that we know about in physics. Of course, there are many more than four. The others just fall within the categories of these four forces. So we'll talk about them in the order that they were discovered or identified by men. So we've got the gravity force, right? This is a force that people are very familiar with. We think of the apples falling out of the tree. We understand now that the moon goes around the earth goes around the sun, the galaxies held together by this force. It's an incredibly significant force in our world around us, and yet it's a very, very weak force on a local level. We have a lot of trouble understanding gravity. We have some mathematical predictability with this force of gravity, but we aren't still quite sure why things having mass attract other things that have mass. We'll talk about this force quite a bit more when we get to chapter 11, where we will talk about Newton and his universal law of gravitation. The electromagnetic force is the one that basically rules pretty much everything you do in chemistry, right? You've got protons and electrons, positive and negative, and they have an attraction to one another, and this ultimately leads to the structure of the atom and the ionic bonds and even the covalent bonds, the sharing of electrons. And this is basically what holds everything larger than an atom together. And so it's very important for our world, our universe, for there to be, you know, trees and people and planets and all of that good stuff. So the electromagnetic force. So these were the two forces that were understood for quite a significant amount of time until we came up with two more, which were difficult to identify and are harder for us to wrap our head around because they don't affect the everyday things in the same way these two do. So the weak nuclear force, about the time they started investigating atoms and discovering that some of them were radioactive and had this stuff called radioactive decay, we could not explain radioactive decay in terms of gravity or electromagnetic forces, so there needed to be another force to explain this. Radioactive decay took place inside the nucleus of the atom, and so they started to give this a name about the nucleus. But the reason there's the descriptor weak is because they then later found a second force inside the nucleus, which is stronger. So we have the strong nuclear and the weak nuclear. And the strong nuclear is really the one that has to be there. Again, both of these forces, it came up that they had to be there because we couldn't explain things with the other forces that we had. So the strong nuclear has to be there because we understand now that there's more than one proton in the nucleus, and they are very, very close together. And the electromagnetic force tells us that two positive charges like that should repel one another. And if they are that close, they should repel each other with a very, very strong force. But they don't. They stay together in the nucleus. So there must be something even stronger holding them together in there. And that's what we call the strong nuclear force. So there are many other forces that we will deal with. In fact, we won't deal with these four hardly at all, except for the gravity one. But when we talk about the many different forces we'll talk about, from friction to the normal force, understand that they all fundamentally come from one of these, or sometimes several of these four fundamental forces. And there's nothing special about four. Again, if you went back 150 years, we would have only talked about three or two of these. And it's possible that in another 10 or 15 years, we'll find another fundamental force, but this is what we have right now. So as we learned last chapter when we talked about two-dimensional motion, forces obviously can be applied in two dimensions as well. Here we have a man pulling a wagon in two different directions, pulling over but also pulling up, and so this force then would need to be split into the part that's going to affect the horizontal movement and the part that's going to affect the vertical movement. So be aware of that. We're going to need to use a little bit of the trig that we learned in chapter 3 to resolve forces and look at them in those two different directions. So we're going to cover a little bit of the history of forces, and this is important because many people today have a misunderstanding of forces and how motion is caused and what it takes to have motion. And a lot of that has to do with the history and the past confusion that has occurred that people have just never learned to correct with more modern data. So we go back in the history of science, and particularly in the history of forces, and we go all the way back to the Greeks, who were some of the first people to try to systematically study and understand the world around them. And one of those Greeks was Aristotle. He was called a natural philosopher, which is what they called scientists at the time. This idea that there's natural motion, stuff that is naturally going to move in a particular direction, rather up or down. And then there's violent motion. So Aristotle would have said something like, you know, rocks naturally want to go down. If you pick up a rock and let go of it, it'll fall, okay? And smoke naturally wants to go up. But you can force both of those to do something different, right? You can take a rock, you can throw it up in the air. You can take a blanket and you can push smoke downward. And that is what he would have defined as a violent motion. We as humans or some other agency forcing the motion to be different than it was supposed to be. But ultimately, he concluded that everything wants to be at rest. Everything wants to be at rest. And again, he would explain this by saying, you know, if you throw a rock up in the air, it goes up for a while, but then it falls back down. and it eventually stops moving, right? And even if you kick a ball along the ground, it'll roll for a while, but eventually it will stop moving. So he had a lot of anecdotal evidence, a lot of evidence all around him that led him to this conclusion. Everything wants to be at rest. There's a preference for all objects in the universe to stop moving if they are moving. And again, we have a lot of real life experience with that on Earth. And this is the confusion that persists to this day, in part because of our real life experience. But I believe if you went out on the street and you started questioning people and asked them if this statement was true, I believe as many as 19 out of 20 people would say, yeah, everything wants to be at rest. That's my experience. That's how science works, and it's not correct. But it was very hard to show that Aristotle was not correct, and one of the reasons for that was Aristotle's ideas were accepted for a very long time. He also came up with, this heavy stuff falling he called gravity, and light stuff rising he called levity. So you see the ending of those words very similar. We still use gravity today to say that stuff with mass falls. Levity still has a light type meaning, but not in terms of science anymore, right? We talk about jokes and stuff being levity. But the real problem with Aristotle was not that he was absolutely totally convinced that he was right. He was a reasonably good scientist, understanding that he was prone to be incorrect. All he would have asked was that you show him some data as to why he is wrong and why your model was right. But unfortunately, the people that followed Aristotle were not necessarily scientists in the same sense, right? The Greeks did a lot of science, but if you follow world history, particularly in Western Europe, after the Greeks, there was a number of different groups in charge that did not do very much science for a very long period of time, eventually to a point where very few people knew how to read and write even, let alone to do science. And so his ideas, however, were preserved, and they were repeated, for hundreds, thousands of years. And at that point, people said, hey, we've been saying this and people have been believing this for so long. It's just got to be right, to the point that questioning Aristotle became unacceptable in some cases. And so when scientists began doing science again in the Renaissance and they found that Aristotle's idea was incorrect, it was very difficult for them to be able to state that without being at great risk even of their lives for saying that Aristotle was wrong, because the political authority of the day had embraced Aristotle as being correct. So Copernicus was one of the men who figured out the errors of Aristotle. And again, Aristotle, all scientists make errors. If you think modern scientists don't make any errors, that's just because we haven't figured them out yet. We're all trying to just understand the world around us, and all of our attempts are an approximation, and approximations are close, but they are not perfect. And so ultimately, someone will come up with a more accurate approximation that will show that part of our current approximation is incorrect. So Copernicus was an astronomer. He studied the stars, and what he concluded from his studying of the stars, in particular the planets, which planet is a Greek word for wanderer, because that's what the planets effectively do. They wander around the sky, unlike all the background stars, which behave very predictably. Copernicus concluded that the sun was actually at the center of the solar system instead of the Earth. And this was a really big issue, right? Because Aristotle said that all things want to be at rest, and the Earth, as we understood it, was by far the biggest thing. And so to say that the sun was in the center of they did say the universe at the time, today we would say the solar system, means that this very, very large Earth that we live on is actually moving, and it's been moving, and it keeps moving all the time. And so that's greatly in opposition to Aristotle's idea that everything ultimately wants to slow down and stop moving. Now, I'm not sure how Aristotle would have dealt with the fact that the sun rises and sets every day, but that was apparently not part of his problem. Or there was a time when they had separate laws of physics for what happened in the sky versus what happened here on Earth. That's part of why astronomy has a separate name from the rest of physics, even though it's really pretty much the same thing. So I don't know if you've ever seen a picture like this with the star streaks, but this is what happens if you point a camera at the sky and you take a long picture. Not a few milliseconds like we normally take a picture, but a long picture, like minutes or even hours long. You will see these streaks of light in the sky, and that is because all the stars appear to move as the night goes on. Now, we would understand today, with our greater understanding of physics, that actually the Earth is rotating and those stars are staying relatively at rest compared to us, and that's why this apparent motion occurs. But they saw all these stars going in perfect circles except for the planets. Now, I made a big blue dot there to represent my planet, and when I hit the button, you see that planet move all over the place. And again, because we understand better today what's going on, these planets are also orbiting the sun, but they're orbiting at different speeds than we are. So they don't do the same thing in the sky every night, because sometimes they're ahead of us in their orbit around the sun, sometimes they're behind us in their orbit around the sun. If you've ever heard of the morning star and the evening star, those are both descriptions of the planet Venus, which is sometimes up in the morning and sometimes up in the evening. It just depends where it is in its orbit and where we are in our orbit as to which place it ends up being. So here we see the two different models, the heliocentric with the big orange dot, the sun in the center, and then all the known planets orbiting around it. And then the geocentric one, the little blue dot in the center, that's the Earth, and the sun going around the Earth, and then all these other planets doing strange things to account for what they actually do in the sky. And you see some of them end up appearing to go backwards for a while, and that sort of thing. It's very perplexing. And Copernicus, once he had collected enough data, decided that this is a much simpler and easier explanation of what's going on than forcing the Earth to be in the center and making Mars go backwards at times and forwards at times and follow all kinds of odd motions. But this was very unpopular to say in his day. Galileo agreed with Copernicus, and he also did a number of experiments and investigated forces and motion significantly. Galileo did not invent the telescope, but greatly improved the telescope and used it to look at the planet Jupiter and see the moon, the biggest moons of Jupiter going around it, and seeing that functioned just like the solar system model. Many times Galileo is pointed to as kind of the father of experiment. He was one of the first ones to do, not just to observe nature, but to test things in nature and to experiment to see what would happen if he changed just one variable. So, and in the course of those experiments, he discovered something that really explains why Aristotle is wrong and the proper way to think about things. And that thing is friction. So you can see from the pictures down below the words here on this slide, what he did is he had a bowl or he had some kind of device, and he put a little ball in it, and the ball would roll down to the bottom of the bowl and then roll back up on the other side. And he found that if he changed the steepness of the sides, that didn't really affect. The ball would still roll almost back up to the same height. And the smoother he made the bowl and the smoother he made the ball, the better it would get at getting back to the original height. So then he, theorized, well, what would happen if I roll the ball down the first hill and I just have a really wide bottom of the bowl before it gets to the other side? If the ball is still going to roll up the other side to the same height, it's going to have to roll all the way across the bottom of the bowl without slowing down, so it has enough oomph to get up the other side. And that's very different from what Aristotle said. Aristotle said that objects want to be at rest. And here Galileo has an object that should just keep rolling and not stop, because it needs to have that motion to be able to climb the hill on the other side. Now, if you actually do the experiment, you find the ball does slow down on its way across the bottom of the bowl. But Galileo was able to conclude and to articulate that the reason the ball is slowing down is because of something called friction, because the ball is rubbing against the surface and the surface is rubbing against the ball, and that is taking away some of the motion. And if we had a smooth enough ball and a smooth enough surface, and we have examples of that today, right? If you've ever played air hockey, or if you've ever seen a puck of dry ice or something like that that can slide with very, very low friction, it does appear to move across a horizontal surface without any reduction in speed, because we've been able to make the friction very, very low. So we had Aristotle, who started with this idea everything wanted to be at rest. Then we had Copernicus and Galileo. And finally, we get to the final individual in this, and his name is Newton. And Newton freely acknowledged within his lifetime that the work that eventually became known as Newton's 3 laws of motion, he freely admitted that most of that work got done by other people. He just did the last little part, and he wrote them down in nice, neat, understandable laws. But he has a famous quote that he's known for saying, which is, if I saw a little further than others, it's because I stood on the shoulders of giants. And when he's saying that, he's speaking of Galileo, he's speaking of Copernicus, he's speaking of those who studied motion before him and studied forces before him. But they ultimately have his name on it, the 3 laws of motion, which is really what this chapter is about, and will help us to understand motion and how forces affect motion and cause motion to change. So we have the first law, Newton's first law of motion, and that says that an object in motion will stay in motion, but an object at rest will stay at rest unless they are acted on by an outside force. So the first part is the hard part to believe, right? That an object in motion will stay in motion. We don't have a lot of experience with that in life. Again, Aristotle would point to a whole bunch of life examples, right? You kick a ball, or you put a leaf on a stream, or whatever, and it's eventually going to end up stopping. So what is this idea that an object in motion will stay in motion? The second part's very easy for us to believe. Nobody questions that objects at rest will stay at rest. We see that all the time. In fact, if an object was at rest and it suddenly starts moving, we get very disturbed, because that's not normal. That's not the way things are supposed to be. So he makes these 2 statements: moving things move, still things stay still. But then he gives the exception, right? Unless acted on by an outside force. And the reason we don't see the first part of the first law occurring very often in our lives is because we're surrounded by outside forces. There's lots of outside forces that are affecting the objects around us when they're moving and causing them to stop. A big one is this friction, right? Because we live in a very full world. Even when you sit there and look around you and go, oh, this room's not very full. Well, it's actually very full of air, and you can't see that air, but that air is present, and it's in the way. And when you throw something through the air, it's got to push its way through the air, even though you can't see the air, and that air is going to slow it down. It's a form of friction, and the surfaces have even more friction than the air. So a rolling object's going to stop even faster than an object thrown through the air. And then you also have this force. We spoke of it as an acceleration last chapter, but really it's a force, the force of gravity, that is pulling everything down toward the surface. So if you throw a ball through the air, it's eventually going to come down and hit the ground, and then it's going to have the friction of moving along the ground instead of flying through the air. So it's all these outside forces that cause the problem with the first law. So examples of the first law. If you were in class, we would do a number of examples. I would set up a tablecloth with a bunch of dishes on it, and I'd pull the tablecloth out from underneath the dishes, and I would say these dishes have mass and they're at rest and they want to stay at rest, and this is an example of the first law. But I can't show that to you, so you can go watch the video of somebody doing it. He's not explaining it in terms of physics. He's presenting it as a magic trick. But remember, almost all magic tricks are nothing but physics that you as the audience don't fully understand, and this is one of them. So go watch that video for a moment. This is also called the law of inertia, and if you go and watch another video. We have a number of short videos here. Again, if you were in class, I would be showing these to you in class because they're that important. These Eureka videos, which is what you're about to start watching, and you'll watch a number of these over the course of the semester. Very, very useful pictorial representation of these physics concepts created for Canadian public television. I like it because it's in English. I also like it because it's Canada, so it uses metric units. But go watch that 5-minute video about the law of inertia, and then come back and we'll talk about what inertia really is and how we measure it and why we call this the law of inertia. So they defined inertia in that video, and we can define it as well as the tendency to do what you're already doing, or being lazy, right? Change takes effort, change takes something to cause it to occur. If there's no impetus, nothing trying to cause change, then there isn't going to be change. And if an object is already moving, then it is moving, and to stop moving is a change from its current state. So objects in motion will stay in motion. And again, this is not unheard of in our universe. It's just very unusual on our particular planet. If you go up in space, as they use the example in space, we've been able to observe all kinds of things in space that tend to keep moving at a constant rate. If you think about the astronauts that went to the moon to explore the moon, their spaceship, used rockets to get off of the Earth and got going toward the moon, but they did not fire their rockets all the way to the moon. Not like when you're driving down the interstate, you got to keep your foot on the gas pedal and your engine needs to keep running the whole time because you're pushing against air. In space, there is no air. There's a vacuum. There's a lack of particles. They coasted all the way to the moon. They actually had to fire their rockets to slow themselves down when they got near the moon, or they would have flown right past the moon. So this is real in our universe. It's just not within the realm of our experience very much. Again, the second part is objects at rest, staying at rest. That's very much in our experience. But the idea that objects in motion would stay in motion if we didn't have friction and gravity doing things to cause them to slow down, it is hard for us to wrap our brain around, but that is what the first law says. That is what we can experiment and demonstrate over and over again in the laboratory. So how much inertia is there, right? How much inertia? Does everything do this equally well? And of course, it doesn't take very long to think about your life experience to know that no, not everything does this equally well, right? You got a leaf sitting on the grass and you blow on it and it'll move, right? It was at rest and it would like to stay at rest, but it's got so little mass that a small, puff of air from your mouth is enough to make it move. On the other hand, a semi-truck or a mountain has an immense amount of inertia, and it would take an enormous force to get that inertia to get that object to begin to move. So ultimately, our inertia, how much resistance to change we have, is a function of how much stuff we are made up of, and this stuff we measure with something called mass, right? The stuff that we're made up of is called matter, and we measure how much matter there is with this quantity that we call mass, whether we're talking about grams or kilograms, or as I mentioned, the English units of mass are stones and slugs, but it's how much stuff makes you up. And in that second video you watched about the measurement of inertia being mass, they talked about a lead brick and a styrofoam brick, and they emphasized that it's not the size, it's not how much space you take up, it's how much actual stuff you have, because styrofoam takes up a lot more space, but lead has a lot more mass. So Newton's first law, the law of inertia, objects tend to stay at rest if they're at rest, they tend to stay moving if they're moving, unless acted on by an outside force. And the more mass they have, the better they follow this law. The better they follow both parts of the law, right? So if you walked out in the parking lot and it was a tricycle, you could give it a kick and you could get it moving pretty fast, right? Or if a tricycle came rolling towards you, you could stop it without too much effort, right? But on the flip side, if there's a semi-truck with a full trailer on it and you went out in the parking lot and you tried to get it moving and it was sitting still, that would be very difficult, right? And on the other hand, if that semi-truck was rolling towards you, it would be very difficult for you to stop it. So this inertia plays on both sides, both the at rest staying at rest and the in motion staying in motion side of things. So we do see the first law working more often than we maybe think it would here on Earth. And that's because of something called equilibrium. You learned about equilibrium when you took chemistry, the idea of a chemical reaction being in equilibrium where the forward reaction and the backward reaction are happening at the same rate, and therefore the same amount of product and reactant are being created at the same time. So it looks like nothing's happening, even though something is happening, it's just canceling itself out. The same thing can happen with forces, right? So technically the first law would work when there are no forces, right? Because the exception at the end says unless you're acted on by an outside force. So again, that rock flying through space would be a true case of the first law. There's no force at all on that rock, and so it's going to keep doing whatever it's doing. But we get lots of cases here on Earth where we have more than one force present, and because they cancel each other out, we continue to follow the first law. And that's what equilibrium means in a force context is all the present forces cancel one another out completely, and so there is no total force. There's no what we call the net force. Again, if you think about that term, net, they use it in chemistry to talk about the net chemical reaction. They also use it on your paycheck, right? You get gross pay. Say you work 20 hours at $10 an hour. That's 20 times 10, that's $200. You don't get paid $200 at the end of the week. There's state tax and federal tax and social security tax and all those things that get subtracted out. And so then the number at the bottom is your net pay. So the number at the top, which is your hours times your rate, that's your gross pay. The number at the bottom is your net pay. And net basically means after the cancelization, after the reductions, after the stuff that gets subtracted out. And it means that in terms of the forces also, the net force is the force we get after we've done all the other canceling out. So if when we do all the canceling out, we end up with nothing left, if all the forces cancel, then we can apply the first law. So let's look at how this works. Let's think about a desk sitting in our classroom. So we've got a desk sitting in the classroom, and it's sitting there, and it's at rest, and it stays at rest. And so you might immediately say, oh, well, there's no forces acting on the desk. But a few moments of reflection will help us to realize that's not true. There are forces acting on this desk. If we picked the desk up a foot off the floor and let go, it would fall to the floor because gravity pulls it downward. And gravity doesn't stop pulling it downward just because it strikes the floor. Gravity continues to pull it down, but it stops moving downward. So there's a gravity force pulling it downward, but there's a force from the floor pushing it up. And that's what we call a normal force. And the normal force, it's a somewhat odd name to give the force, but it comes from mathematics. In math, you learned perpendicular. Perpendicular means that there's a line that makes a right angle with another line. And because math people are very picky about these things, perpendicular means a line perpendicular to a line that makes a 90-degree angle with a line. But if a line makes a 90-degree angle with a plane, then that is not called perpendicular, but that is called normal. Normal, a 90-degree angle to a surface is called normal to a surface. So that is why we call it the normal force, because the normal force will always push out of the surface perpendicular, right? Even if, so we think, well, what does that mean? That means normal always pushes up. Well, that's not true. If you're on level ground, normal will push up. If you're on a hill, the normal will push straight out of the hill. And that does not perfectly cancel gravity in that case. And that's why things slide or roll down hills. But if you're on a flat surface, gravity pulls down with some number of newtons, and if the ground is strong enough, it will push up with that same amount of newtons. The normal force is a very flexible force, right? As long as the surface is strong enough, the normal force will keep getting bigger, and it will be just as big as it needs to be to cancel the other vertical forces and cause no vertical motion. So a lot of times we don't get vertical motion if the object is resting on the ground. because the normal force is so adjustable. So we got a desk. Let's say the desk is 150 newtons in weight. So there's a gravity force of 150 newtons down. There's a normal force of 150 newtons up. Those two cancel each other, right? 150 minus 150. The down force is negative. The up force is positive. You add those together, you get 0. So the net force on the desk is 0. So now we can apply the first law. All the forces cancel out. The object was at rest. It's going to stay at rest. Okay. If I lift the desk up in the air and let go, it's not in equilibrium anymore. Gravity's pulling down with 150. Nothing's pushing up because it's in the air. So it's going to accelerate downward and it's going to move and it's going to have a net force on it. So its acceleration is going to change and it's going to move. Okay, so then now it's not following the first law. Another example would be a skydiver. You've probably heard of skydivers. You've probably heard of something called terminal velocity for a skydiver. So they jump out of the plane and similar to the desk, gravity is pulling them down and so they speed up toward the ground. But as they speed up toward the ground, they are pushing through the air at a very high speed and so the air pushes back. And the faster you move through the air, the faster the air pushes back. And that is, if you don't believe this, just think about when you were riding your bike, how hard the air pushed against your face. Think about when you put your hand out the window of your car, how hard the air pushes against your hand. And then if you've ever put your hand out the window of the car when you were on an interstate driving at a high speed, how hard the air pushes against your hand. Air resistance is proportional to velocity. The faster you go, the more resistance you experience. So the skydiver eventually gets falling so fast that the upward force of air resistance and the downward force of gravity are equal in size. So now there's an upward force just as big as the downward force. And what one has to be careful about is that equilibrium does not mean you stop moving. Equilibrium means you stop changing your movement. So the skydiver is falling at a very high rate of speed, but this skydiver stops increasing that speed. They've reached what we call terminal velocity, their final velocity. They're not going to go any faster than this because the forces are now equal and canceling out. Another example would be a car driving down the highway with its cruise control set, right? You've got the weight of the car pushing down. You've got the normal force pushing up on each of the 4 tires. Those cancel out. You've got the engine applying a forward force. You've got friction applying a backward force. And you've got the computer of your car applying just enough engine force to keep the velocity constant, right? That's what cruise control does. So that's an object that's in motion and it stays in motion because all the forces have canceled. Likewise, the skydiver's in motion, stays in motion at the same speed because all the forces cancel. So those are both examples of the first law working on Earth, not because there's no force, but because the forces all cancel out. So we've talked about friction quite a bit already. So just to go a little bit deeper into this concept of friction, it comes from surfaces rubbing together, rubbing past each other. You can think of it on a very tiny scale. You can think about something like a ball pit. And when you wade through the ball pit, you've got to push those balls out of the way. And that takes some effort, takes some energy, and pushing the balls out of the way causes you to slow down a little bit. And that's really what is happening in terms of friction. You can also think about it in terms of Velcro. You know, the Velcro's got one side of the Velcro is a whole bunch of hooks and the other side of the Velcro is a whole bunch of eyes. And so the hooks catch in the eyes and they catch on one another. And that's how Velcro holds itself together. Well, that's really what's happening at an even smaller scale for friction, right? You have these two surfaces. Even if the surfaces look smooth, they're really not. They're rigid at a very small scale. And then they catch on each other as they rub past each other, and that costs us some of the motion, costs us some of the oomph to the movement. And so you slow down when you're sliding. You don't slow down once you've already stopped, right? Because there's not the motion between the surfaces, although that friction between the surfaces can initially prevent you from starting to move, right? When you first start to push on an object, you might push on it with some force and it still won't move, and that's because there's friction between it and the surface. So again, very hard to see the first law on Earth because friction is present. It's that outside force that's spoken of at the end of the law, and it's almost always there here on Earth, and therefore it's messing with us and preventing things from staying in motion. That friction can come from a solid, a liquid, or a gas. This solid friction is greatest, right? If you have two solids rubbing against each other, you're going to create much more friction. Liquids are less, right? Sometimes we use liquids to reduce friction, like oil used as a lubricant to reduce the friction between moving parts. And obviously gas friction is the lowest, right? So air resistance is still friction, but air resistance is so much less than the other two, right? If we could, we would levitate our trains, we would levitate our cars, and we would move through the air and not move along the surface because the friction would be so much less, and therefore movement would cost us less energy, less effort. But of course, there's the flip side to that, right? It's the astronauts going to the moon. Yes, they didn't have any friction or very little friction, but then that means when it comes time to stop, you have to make the effort to stop. We become very used to friction on Earth and using friction. I was just taking a bike ride with my sons this morning, and we were coming up to a road, and I told them, because one of them is very new to riding a two-wheeler, I said, hey, we need to start slowing down for this road. And so we just didn't pedal for a little bit, and we slowed down and stopped in plenty of time before we reached the road, because we use friction like that to help us out. But if there was truly no friction, we would have to put forth effort to slow ourselves down. I just mentioned this idea of static versus sliding. So when something is moving, it has sliding friction, or what's called kinetic friction. When something is stationary, then we have what we call static friction. And the static friction is greater than the sliding friction. You can think of Velcro. If you had Velcro sliding across each other, yes, it would catch some, and there would be some resistance, but you would not have as much as if you took the two pieces of Velcro, you shoved them together and held them together for a moment, and then you tried to slide, right? If you stick them together and let them stick together, then they're going to really entangle with one another, and then it's going to be much harder to rip it loose. I had experiences building snowmen as a kid, right? And you'd be rolling that big ball that you were going to make the base of your snowman, and you'd be rolling it and rolling it and rolling, and it would get bigger and bigger and bigger. And I would realize that I had to keep pushing, because if I stopped pushing, if I let that ball come to rest and sit still, it was going to be too heavy for me to get going again. But if I had it going, it would keep moving. I could keep it moving. But once it stopped and settled in, it was going to be stuck, and that was just where the snowman was going to have to get built. So that's just an example of static versus sliding that might relate to your own life. If you built snowmen as a kid, if you lived too far south and never got to build big snowmen, then you can't relate. So we move on then to Newton's second law, his second law, and this is the one that really connects the idea of forces to the motion, and numerically calculates how much motion we're going to get due to a force. So this first law is very conceptual, right? If you don't have forces, then you'll keep doing whatever you're doing. If you do have forces, then you won't. The second law is very precise and very mathematical. In fact, it's really a mathematical equation is what it really is. I joke, it's the quickest law you can ever write, because you can write it with as few as 5 or 6 pencil strokes if you don't want to lift your pencil off of the sheet, because all you got to do is write this formula. And I have found that in my, this is not a scientific study, of course, but in my anecdotal experience asking people about physics, because they find out I'm a physics teacher, so then I ask them about their physics experience. This is the number one item, probably by a factor of 3 to 1, the number one thing that people remember from physics. If I say, hey, what's one thing you remember from your physics class? More than anything else, they will say, they won't say Newton's second law. They'll say what Newton's second law is, because we're going to use it a lot, and it comes up a lot, and it's a very important concept. So this is the mathematical relationship between your inertia, how much mass you have, how much force is being applied to you, and then how much you're going to accelerate, or how much your motion is going to be changed. So here it is in words. The acceleration that a force produces is directly proportional to the size of the force and inversely proportional to the mass of the object on the object. should be the mass of the object. So we have acceleration, and the bigger the force, the more acceleration we're going to get, right? That's that word, directly proportional. And we learned this in math, right? Directly proportional means that when one gets bigger, the other gets bigger. But then it's inversely proportional to the mass, right? So when one gets bigger, the other gets smaller. So we take the force and then we divide it by your mass, and that tells us how much you'll accelerate. So if I apply a huge force to you, you're going to accelerate, okay? If you're small, I can accelerate you a lot even without a huge force because I'm dividing by a very small number, which is going to give me a bigger answer, okay? But if you're very, very, very massive, then a force is not going to cause you to accelerate very much. In fact, I might need a very large force to even get you to accelerate at all because of the amount of friction involved. So this is really the mathematical expression that these words are describing, just the directly and the inversely relationship to these things. But we don't like division, so we're going to end up rearranging this, right, from A equals F over M. We're going to bring the M to the other side so that it's all multiplication. So this is the form that people usually remember the second law in. F equals MA. The force applied to an object is going to equal the product of the object's mass and its acceleration. It's a little bit misleading because really the size of the force is determined and the mass is the determinant, and the acceleration is really the variable part here. But we like to write it this way. One year I had a student look at this equation and they kind of squinted and they said, hey, you look at that equals sign, it kind of looks like a capital E. So that makes this the FEMA equation, the Federal Emergency Management Agency equation. And I said, hey, you know, if that helps you remember it, then that's great. You know, the FEMA equation, if that helps you. F equals MA. So a couple of quick concepts. We already talked about this a little bit, but this means it's going to be hard to accelerate you if you have a lot of mass. So you see there a picture of some concrete blocks. Concrete blocks are very hard to accelerate because they are very, very massive. That's what F equals MA says. It also says that if you don't have very much mass, you're going to be easy to accelerate, right? A feather is going to be easy to accelerate because it has very little mass. Now that's a little bit misleading, maybe, because you might have some real life experience where you tried to throw a feather and you couldn't get it to go very fast. But that was of the fact that the feather has a lot of air resistance because of its large surface area. But it is easy to accelerate in the absence of another force working against you, like air resistance. So again, the second law, F equals MA, you can think about sticking different numbers in there, and we will do some practice problems with numbers here in just a moment, but that's really what it's all about. So what are the units of force? So the unit of force is the Newton. I talked about this in some previous chapters. I've talked about it already in this chapter. The unit of force is the Newton. Again, Isaac Newton came up with these 3 laws of motion, and so we've named the unit of force after him. The unit of force is the first unit that we've come across that is what we call a derived unit. It's really equal to some other units that are normal units, right? We don't really think of what a Newton is. A kilogram, a meter, a second, those are basic units. A Newton is a derived unit. It's a combination of basic units. So anytime you want to know what a unit is equal to, you just go back to the equation that you got it from, right? So this is our equation, FEMA, F equals MA. So F equals mass times acceleration. So if we want to know what a Newton is equal to, we look at what the units on the other side of the equation are. So mass is measured in kilograms in physics. Acceleration is in meters per second squared. So a Newton is a kilogram meter per second squared. Now, could we go around saying 54 kilogram meters per second squared? We could, but that's kind of a mouthful, and it's nice to have a shorter, simpler way to say it. So we just say 64 newtons, and that's it. So if we have 1 kilogram and 1 meter per second squared, we multiply them together and we would get 1 Newton. This is the official SI or System International unit of force. It's the Newton. It's around 1/4 pound, actually slightly more than 1/4 pound, or slightly less than 1/4 pound, because 4.45 of them make up 1 pound. So if you go to calculate your weight in newtons, you're going to get a number that's almost 4.5 times bigger than the number you get in pounds. Again, that doesn't mean you weigh more. It's just a fact that if you use a smaller measurement, you're going to use more of those units to measure the same quantity. So one very common example of Newton's second law is what we call the weight equation. How much do you weigh? Well, your weight is how much force you put downward due to the downward pull of gravity. So we can take your mass, we can multiply by the acceleration of gravity, which we learned before was the value of 9.81 meters per second squared on Earth, and then that will tell us how much force you will put downward on the scale or on the ground or on the floor or wherever you happen to be standing. So unfortunately, weight is represented by a number of different symbols, right? So you might think weight, well, we use capital W. Well, sometimes we use capital W, and sometimes we say it's the force of weight, and sometimes we say it's the force of gravity. So you just need to understand that all three of these symbols are equivalent to one another, and sometimes you'll see one and sometimes you'll see the other. But really, this is Newton's second law again, right? The weight is a force, mass is a mass, and gravity is the specific acceleration in this context. Now, usually what I will tell you about Newton's second law is that you need to be very careful about using it, right? An object can be pulled on by a bunch of different forces, right? You can be pulled left and right and up and down, but the reality is you can only accelerate in one direction. There's only one direction that your motion can be in, and there's really only one direction your motion can be changing in at a time. So although you can have forces in a bunch of directions, you can only have acceleration in one direction. So what that means is you need to take all the forces acting on your object and put them together, and then have the one single net or final force from all of them, and use that to do F equals ma and find your acceleration. So here's an example. If you had a 2 kilogram object sitting on that scale, 2 times 9.8 meters per second squared would give us 19.6 newtons as our force, our weight of the object. So just take a moment now and go watch the weight video. Again, this is linked in the comments of the YouTube video. It's also in the notes section of the PowerPoint on this particular slide. So you can go either place to get the link. Go watch the weight video, and they will talk about the difference between weight and mass, which if you aren't wondering that, you should be wondering that. Why do we have them both? Why do we care? So the video took you to the moon and pointed out that your mass is the same everywhere in the universe, but your weight changes depending on what the gravitational pull of your current location is, your current planet, your current object. So you would weigh, this person weighs 560 newtons on the Earth, but they only weigh 90 newtons on the moon. That's because the gravitational pull on the moon is 1/6 of what it is on Earth. If you go to Mars, it's 1/3 of what it is on Earth. If you go to Jupiter, it's 3 times what it is on Earth. It's different on different planets. For those of us who spend our entire life living on the Earth, is it going to matter that there's a difference between weight and mass? Maybe not, but we are learning physics, and we are learning physics beyond the immediate scope of where we live. So that's something to consider. Friction is another thing we've talked about a bunch already. Now we're going to look at the equation for calculating friction force. So you might think, well, heavier things have more friction, and that's generally true. But when you go to do the calculation of friction, we have the force of friction is equal to the normal force times this coefficient of friction. And that's just a coefficient. The normal force is in newtons, the friction force is in newtons. This is just a coefficient. Obviously, if you're being dragged across a very rough surface, there's going to be more friction, so this coefficient is larger. If we're dragging you across, very smooth ice, then this coefficient is much lower. This is what's dependent upon the surfaces. Okay, this is the object, right? If I'm dragging a dead buffalo across the ice, it's going to be harder. If I'm dragging a mouse across the ice, it's going to be easier, right? That's where the normal force part comes in. But people go, well, why the normal force? Why not the gravity force? Well, this is because when you drag something across a surface, sometimes there's something holding it up, right? And if there's something holding it up, then it's not being pressed into the ground quite as much. So you can think about that picture we saw on a previous slide of the man pulling the wagon at an angle, right? So when he pulls the wagon with his daughter in it at an angle, he's partially lifting the wagon off of the ground. And that means the wagon's full weight is not being pressed into the ground, and therefore there's not as much friction between the wagon and the ground. So that's why we use the normal force. And again, the normal force is very flexible, right? So if you have an object that weighs 120 newtons, but we're pulling up at an angle such that we're lifting it with 30 newtons of force, the normal force is going to shrink from 120 down to 90 just to hold up whatever's left of that force. And because there's less of the weight pushing into the ground isn't pushing back as hard, there's going to be less friction. So that's why it's appropriate for us to use the normal force, and that's why the normal force gives us the correct value. As I just said, the object is what determines the size of force normal, and the surface just determines the size of mu. Mu is very rarely over 1. If if the coefficient of mu is greater than 1, that would mean it takes more force to drag it than to lift it. And that's just not a very common occurrence in our world. So mu is usually between the value of, say, 0.1 and 0.6, somewhere in there. It's going to be a decimal between 0 and 1. So now we're going to do a couple of practice problems. So if you were to push a 55 kilogram box across an ice-covered pond with a force of 125 newtons, what is its acceleration? So oftentimes in physics, when we say things like an ice-covered pond, we are wanting you to assume there is no friction. And since no mu was given to us in this problem, it's reasonable for us to assume there's no friction here. So how do we approach these problems, right? We talked about the problem-solving methods back in chapter 2. So one of the big problem-solving approaches that you're going to take for force problems is to draw a picture and to draw in all the forces that are present. This is really, really important because we're almost always being asked for the acceleration, and the acceleration we're going to get from the net force, right? We're going to find the net force, divide the net force by the mass, that will give us the acceleration, F equals ma. That's Newton's second law. But in order to get the net force, we have to add all the forces together. And to do that, we have to make sure we have all the forces. If we're missing some of the forces, we're going to end up in trouble because our total force isn't going to be right because we're missing one. Whether that's one that would add or one that would subtract, that's not the point. The point is if we're missing one, we're missing one. So drawing the picture and going through and processing what is going on in this picture, what are the different things acting on this object, is very important. So we call this a free body diagram. A free body diagram, you draw a little picture of the object. Doesn't have to be pretty, doesn't have to be fancy. It can just be a box that you label, a square that you label, dog. It doesn't have to look right. You just have to draw a little sketch and then label all the forces, draw all the forces and label all the forces. Remember, all the way back to the beginning of this, a force is a push or a pull. So what things are there pushing or pulling on this box, okay? We were told there's a person pushing on the box. So I've got the force of the person pushing with 125 newtons, okay? We know that we're on the earth, so gravity is going to be pulling the box down. So I got force of gravity pulling down, and I'm on a surface, so I've got a force normal pushing up, okay? So those are my three forces. Is there a force backwards? Well, sometimes there would be a friction force backwards, but I'm on an ice-covered pond, so there is no friction, so that one isn't there. So once I have drawn and labeled all my forces, now I got to try to figure out the value of all the forces, right? It's not enough to just know, oh, there's a normal force there. I got to figure out what the number is because I'm going to put all these forces together. So the gravity force is one that we can do, right? Because we have this equation, weight equals mass times gravity. We were given the mass of the object. So if the box has a mass of 55 kilograms, gravity on the earth is 9.8. I can stick the 55 in for the m, the 9.8 in for the g. 55 times 9.8, 540 newtons. That's the gravity force downward. And then we talked about how the normal force is very adjustable, very flexible. If gravity is going to pull down with 540, if the ice is strong enough to withstand 540 newtons, then the ice is going to push up with 540 newtons. The ice is not going to fling the box into the air, and the ice is not going to allow the box to start sinking into the ice if it's strong enough, which we assume that it is in this case. So we have 540 down and 540 up. So those two end up canceling, and that's a very common occurrence. That the vertical forces will cancel. But as you will see here on the third problem, just because they cancel doesn't mean they don't contribute to the answer in some way. So this becomes easy because the vertical forces cancel and there's only one horizontal force. So we add up the horizontal force and we get 125 plus 0 from the vertical, which we wouldn't be able to add like that, right? We'd have to make a triangle if there was actually a vertical force. But since it's 0, it's 0. So the net force is that 125 newtons. We divide it by the mass of the box, and that gets us an acceleration of 2.3 meters per second squared. And that is our answer, right? So we used F equals ma. We took the force, divided it by the mass, and that gave us the acceleration. A newton is a kilogram meter per second squared. So if we divide by a kilogram, the kilogram drops out, and all we have is the meters per second squared that's left. So we divide those numbers, we get that value. So another example problem. A rock has a weight of 225 newtons. What is that rock's mass? So this is a simpler problem. We don't need to draw all of the forces because we're not being asked for the acceleration. We're looking actually for the mass. So this is weight equals mass times gravity. We were given the weight and we know the value of gravity. So we have the W, we have the G, we need to solve for the M. That's what we have as an unknown. We divide both sides by the G. We end up with M equals weight over the acceleration of gravity. We can plug those numbers in and get the mass of the object, okay? Because 9.8 is close to 10, you're usually gonna have a mass that's, 1 order of magnitude less than your weight. So 225 newtons becomes 23 kilograms. That's a good rule of thumb to be checking and making sure that you didn't mess up the math somewhere, that this should basically have one fewer, not really one fewer digits, but this was something in the 200s, so this is going to be something in the 20s for the mass. Okay, so here is a problem in which we have friction, a problem in which we're actually going to end up with 4 forces in all 4 of the directions. There is a problem that can become a little bit more difficult than this. If we'd been pulling the sled upward at an angle, then we would have to split that force into 2 parts. And there'll be a couple of practice problems like that on the practice worksheet that I will post on Blackboard for you. And then the answers will also be posted on Blackboard so you can look at how to do some of those problems. So this time we got a 65 kilogram sled with a 0.2 coefficient of friction. It is being pulled with a force of 250 newtons. What is its acceleration? So sometimes we are going to be asked for the acceleration, and we're going to use all the forces to get the net force and the net force to get the acceleration, like we did 2 problems ago, like we're going to do here. Sometimes the problem works in the opposite direction. Sometimes they'll say the acceleration is 0. Or they'll say something a little more obscure. They'll say the object is moving with a constant velocity. But really, when they say constant velocity, they mean the velocity is not changing. And if the velocity is not changing, that means the change in velocity is 0. The change in velocity is defined as acceleration. So if they say the velocity is constant, that's the same as saying the acceleration is 0. If the acceleration is 0, think about FEMA, F equals ma. If the A is 0, then the F is going to have to be 0. It doesn't matter what the mass is, 0 times anything is 0. So then we have a net force that's 0. And that means all of our forces need to add up to 0. So sometimes they'll tell us the sled is sliding at a constant velocity. How hard is it being pulled? And then you would go through this whole process and you wouldn't know that the person's pulling 250, but you would do this whole process and figure out what the friction force is. And you'd say, well, the person has to pull just as hard as the friction force if you're going to stay at a constant velocity. So sometimes you're supposed to find the acceleration. Sometimes you're supposed to work backwards to find the force. But it all comes down to the sum of the forces equals the net force, whether that net force is 0 or not. So we drew our free body diagram, and now we got to go about calculating our individual forces. There are four forces here. There's the force of the person pulling forward. There's gravity pulling down. There's the normal force pushing up, and then there's friction pushing backwards. So there's four forces, but in the problem, they only told us what one of them was. So we have to go ahead and calculate the other three forces, okay? Gravity is pretty easy. Again, force of gravity is mg. That's the definition of weight. They did tell us the mass of the sled, so we can calculate that to 637 newtons. Since there are only two vertical forces, the normal force is going to be just as big as the gravity force. Now, let me say a thing about this angle thing. So if we'd been pulling up such that we calculated that 250 times the sine of the angle was, say, 50 newtons upward, well, then there'd be 637 down, and then the person would be lifting with 50, so then the normal force would have to just lift the rest. So we would take the 637, we would subtract the 50, and we get the normal being 587. So that would make our normal force smaller, and then we're going to take our normal force, we're going to use it to find the friction, so that would make our friction smaller. So that's an important piece when you have an angle involved in the problem. But we don't have that in this particular example, so we get 637 for the gravity, and so then we can just plug the 637 in for the normal. So now we've got two of them done, and then the friction force, that equation from a couple slides ago, the force of friction equals mu times the force normal. Mu was given in the problem as 0.2. The force normal is 637 that we just got, so the friction comes out to be 127. So now we have numbers for each of our four forces. The vertical ones cancel, they don't contribute. The horizontal ones, we got 250 to the left, 127 to the right. So we subtract those, that gives us a net force of 123 newtons. We're then going to take our net force divided by the mass to get our acceleration. Newton's second law, F divided by M, F net divided by M equals the acceleration. 123 divided by 65 comes out to be 1.89 meters per second squared. So again, this might look involved. Again, as you do more of these practice problems, they will get easier. I would encourage you to work that worksheet that I included in this folder on Blackboard before you start doing the homework problems, just to give yourself some extra practice. So the first law was very conceptual. The second law was very mathy. The third law is also very conceptual. Newton's third law. Forces always exist in pairs. If one object exerts a force on a second, the second will exert an equal and opposite force on the first one. It's another example of a physics law that comes into everyday language. People say for every action, there's an equal and opposite reaction. Well, that's missing a really important word. It's missing the really important word on this slide that's in red. For every action force, there's an equal and opposite reaction force. The force is a really, really important part, right? Just because I have a particular thought doesn't mean there's going to be a reaction thought from somebody else. But if I reach out and punch somebody, there's going to be a reaction. The reaction is going to be that they're going to punch me back, right? If you've ever kicked a wall or you've ever punched a wall, you perhaps immediately regretted it because you applied a force to the wall and the wall applies a force back. Same size, but in the opposite direction. So if object A acts on object B, then B is going to act back on A with exactly the same size force. I had a student once say, forces always come in pairs. They're like shoes. Shoes always come in pairs too. So there's this story in physics about this smart horse, this farmer who had a talking horse that was reading a physics book, and he hooked the horse up to pull the cart to town the next day, and the horse said, this isn't going to work, because if I pull on the cart with 500 pounds of force, the cart's going to pull back with 500 pounds of force, and they're just going to cancel. We're going to go nowhere. And the farmer had to figure out how to convince his horse that he could pull the cart. I mean, he pulled the cart yesterday. He pulled the cart the day before yesterday. He knows the horse can pull the cart, but the horse is trying to use Newton's third law to argue that it can't be done. And the key to understanding this, right, we've just looked at free body diagrams. We've just talked about the normal and the gravity force canceling each other out. But the key to canceling out is you need to have the forces acting on the same thing. Newton's third law, force pairs never act on the same thing. A is acting on B. B is acting on A. They're acting on different things. So in order for the horse to move the cart, he just has to pull harder forward on the cart than the friction force pulls backwards on the cart. And as long as he can pull harder than the friction force can, he'll be able to move the cart. And likewise, the cart is not able to stop the horse because the horse's feet push backward on the ground, causing the ground to push the horse forward harder than the cart pulls backwards. So the horse and the cart both get to move toward town. Yes, those two forces, as on the diagram, the two P forces are equal and opposite, whether that's 500 pounds or 1,000 pounds or 2,000 newtons, whatever that number is, they are equal and they are opposite. But one is on the horse and one is on the cart, and therefore they will never cancel out. Lots of wonderful examples of the third law, right? This is why we use a hammer to pound in nails, and we don't just use our hand, because when we hit the nail, hammer hits nail, the nail hits the hammer. If we hit the nail with our hand, then the nail would hit our hand and we would hurt. That's why we use a hammer instead. This is really how we walk, right? We walk by pushing backwards on the ground, and then the ground pushes us forward. That is how we are able to move and motate on our feet. It's because we push backwards on the ground pushes forward. Think about sprinters on a track team and the blocks they have. This helps you to understand that those blocks are set up so they can push backwards on the block and get a good start to running down the road. But also, if you step on a skateboard like this, skateboard will fly out underneath you and you will move forward. This is why guns have a kick, right? The bullet is pushed forward and the gun is then pushed backwards. It's Newton's third law. If a force is going to be pushed forward on the bullet, then another force is going to push backwards on the gun, and then the gun is going to push against your shoulder or whatever you have behind the gun. So this is why guns kick, because of Newton's third law. And then we have what we call reaction rockets, right? You blow up a balloon full of air and then you let it go. The air rushes out of the balloon. The air is pushed downward and out of the balloon. The balloon is pushed upwards. This is one method of moving things, and it's essentially the only method of moving things when you get to space, right? Birds can't fly in space. There's nothing for their wings to push against. The only way to move yourself in space is to throw something in one direction, and then you will recoil in the opposite direction. And that's what we do. Our rockets in space shoot tiny particles of gas out their engines at very high speed, and they shoot them backwards, and then that causes the rocket to move forwards. So that's Newton's third law. So now we've covered Newton's first, second, and third laws. Again, you got a homework, you've got a quiz, and work on that extra worksheet that's in the Blackboard folder as well. And I'll see you back for chapter 6.